This is part two of a series on logic. Um, in the previous section, I committed to presenting the best argument I can to the effect that the rules of classical logic are correct, and specifically that an argument form is valid if and only if it is valid according to classical logic. So the first step in the argument, given what I've said so far, has to be to look at some mathematical notions in an introductory fashion with more rigor than I've afforded them so far. So the purpose of doing this is to develop and define some of the vocabulary that the argument will use. The most fundamental notion I need to explain, and the most difficult to explain, is the notion of a set. I will offer what I consider to be the most mainstream, most widely accepted explanation of the notion of sets. This explanation is what I will call the classical notion of sets, as formalized in first-order logic and the axioms of ZFC, which is Zermelo-Fraenkel set theory with the axiom of choice. So intuitively, a set is a collection of objects. Any object can be in a set, and for every set, every object either is in the set or is not in the set. The relation of set membership, according to the classical notion of sets, is a purely binary in or out affair. Everything is either in or out of every set. Nothing is both in and out of any set. Nothing is neither in nor out of any set. Nothing is in any sense in between, in and out, of any set. Sets can be finite or infinite. Examples of finite sets include the set containing exactly the numbers 1, 2, and 3. The set containing exactly the city god temple of Shanghai, my left hand, and the number 7. The set containing exactly the number 1. And the set containing nothing, also known as the empty set. Examples of infinite sets include the set of all integers, the set of all positive integers, and the set of all sets of positive integers. The set of all sets of positive integers contains such sets as the empty set, the set containing exactly 7, 3, and 4, the set of all positive integers except for the numbers 9 and 20, and the set of all positive integers. Those are examples of elements of the set of all sets of positive integers. No two distinct sets have the same elements, according to the classical notion of sets. For example, there is exactly one empty set. There is exactly one set containing exactly the numbers 3 and 5, and so forth. If two sets have the same elements, then those sets are equal, i.e., they are the same set. This is the axiom of extensionality, which is the first axiom of ZFC. And here's a formal statement of the axiom of extensionality. For all x and y, and for all z, z is in x, if and only if z is in y is true, if and only if x equals y. And so that's just a first-order logic statement, but I've sort of, I'm saying it, and I've inserted some informalities to attempt to aid clarity. Okay, so ZFC is a set of axioms for set theory, one I have just stated the first axiom of. The vocabulary ZFC uses contains two copulas, in, which represents the relation of set membership, and equals, which represents the identity copula, the relation of being one and the same thing as. Thus, the whole vocabulary of ZFC is on display in the axiom of extensionality. This axiom is simply a formal statement of the idea that sets containing the same elements are equal. This is also sometimes stated by saying, sets are extensional. The next axiom of ZFC states that every non-empty set contains a member disjoint from itself, This is the axiom of regularity. And here's my attempt at stating this. For all x, if for some a is in x, then for some y is in x, and not for some z is in y, and z is in x. So in short, every non-empty set has a member which is disjoint from itself. One may rightly ask why one should believe what this axiom says. At face value, perhaps it's not an intuitive truth about sets. It is, however, an intuitive truth about the universe of sets under the von Neumann universe picture of the universe of sets. The von Neumann universe is one way of intuitively motivating the axioms of ZFC. The universe of sets as described by ZFC can be organized into an infinite hierarchy of stages. At stage 0, you have no sets. At each successive stage, you form all sets that can be formed from members of the preceding stages. At stage 1, you have just the empty set. At stage 2, you add the set containing exactly the empty set. At stage 3, you add the set containing exactly the empty set and the set containing exactly the empty set, as well as the set containing exactly the set containing the empty set. So stage 3, right, there are two additional sets. One of them is the set of the empty set and the empty set. And one of them is the set of the empty set. So from here, the number of sets added at successive stages increases extremely rapidly. After the stages 0, 1, 2, 3, etc., going on forever, one arrives at stage omega, where infinite sets start to appear. Then there are stages omega plus 1, omega plus 2, omega plus 3, going on forever. After all of those is stage omega plus omega, also called 2 omega. Then there are stages 2 omega plus 1, 2 omega plus 2, etc., all followed by stage 3 omega, which is similarly succeeded by stage 4 omega, 5 omega, etc., each with infinitely many stages in between going on forever. All of these are followed by stage omega times omega, or omega squared, which is followed by omega squared plus 1, and on to stage omega squared plus omega after infinitely many in between, eventually to omega cubed and omega to the fourth, right, with lots of, infinite sequences in between, right, infinitely many infinite sequences, and so on forever till you get to stage omega to the omega, and then, infinitely many infinite sequences of infinite sequences on forever until you get to eventually omega cubed and omega to the fourth, and so on forever to stage omega to the omega, eventually to stage omega to the omega to the omega, stage omega to the omega to the omega to the omega, and so on forever, and what's beyond that, and so forth. And everything I've laid out there doesn't even begin to cover the tiniest iota of the vast quantity of stages that the von Neumann universe has. And the sets that are produced at the stages we named are such a tiny fraction of all the sets that exist in the von Neumann universe that they are as nothing compared to infinity, only that does not begin to describe the tininess of the portion that I've covered, which can only be understood by deep study of the mathematics of infinity. So in total, the von Neumann universe is a series of stages, one corresponding to each ordinal number, where at each stage, all sets of sets formed at preceding stages are formed. So the vast series of numbers that I began but failed to scratch the surface of in the preceding paragraph is the series called the ordinal numbers. The ordinal numbers may seem to be an incredible concept, but they can be explained in a completely rigorous and formal way by developing them in ZFC. So what I've done so far is not a formal development of the theory of ordinal numbers. Indeed, the whole discussion that I'm currently engaged in about the von Neumann universe is merely intuitive motivation for the axiom of regularity and the rest of the axioms of ZFC. This discussion is merely explanation, an aid to intuition, and does not form a part of any argument. However, everything I am saying is, to the best of my awareness, true according to the classical conception of mathematics as grounded in first-order logic and ZFC. One interesting fact about the von Neumann universe is that in it there are only sets. There is nothing else in the von Neumann universe besides sets. In fact, this is a consequence of the axiom of extensionality, as it is formulated in ZFC. However, this illustrates that obviously the axioms of ZFC are not the one definitive way of understanding sets. For example, it is useful for many purposes to talk about sets containing non-sets. However, a universe containing only sets is quite sufficient to form a foundation for all of math. The axiom of regularity is true in the von Neumann universe, and the axiom of regularity is not usually necessary for doing math. Wikipedia has a lot of interesting discussion about the axiom, covering assorted implications it has. Nothing we will do will depend on the axiom of regularity. I have introduced it only because it is one of the axioms of ZFC, and so to recall, right, that's the last axiom I stated, which states that every non-empty set contains a member disjoint from itself. True in the von Neumann universe, as I said. After the axiom of extensionality and the axiom of regularity comes an infinite series of axioms, stating for every statement P of first-order logic, in the vocabulary of ZFC, that for every set A, there exists the set of elements of A of which P is true. Each statement of first-order logic in the vocabulary of ZFC generates one instance of the axiom schema of specification, stating the same. So here's the axiom schema of specification. Let P be a statement of first-order logic in the vocabulary of ZFC, which does not contain any free occurrences of the variable name y. Then, the following is an axiom of ZFC. For all z, for some y, for all x in y, if and only if, x in z, and p. The axiom schema of specification can be compared to the axiom schema of comprehension. The axiom schema of comprehension is not part of ZFC. It states, for every statement P, that there exists the set of objects of which P is true. The axiom schema of comprehension leads to logical contradictions. For example, it leads to Russell's paradox, the paradox concerning whether or not the set of all sets that are not members of themselves is a member of itself. The logical contradictions that arise from the axiom schema of comprehension have probably been the most major driving force in the development of set theory. The von Neumann universe picture and the axioms of ZFC are an outcome of the following series of efforts, with many others contributing along the way, I'm sure. So, Gottlob Frege's articulation, in essence, of the laws of classical first-order logic in his Grundgesetz der Arithmetik, along with some laws that led to Russell's paradox. Bertrand Russell's and Alfred North Whitehead's efforts to resolve Russell's paradox and rescue the spirit of Frege's project, particularly in their Principia Mathematica. Efforts along similar lines by Ernst Zermelo, resulting in the axioms of Zermelo set theory, and further contributions by von Neumann, Abraham Fraenkel, and I assume others, leading to the axioms of ZFC. The axiom schema of specification is the compromise that ZFC makes to deal with the fact that the axiom schema of comprehension is logically contradictory. Rather than letting you form any set you can describe, ZFC tells you that you can only form any subset you can describe of any existing set. This appears to block Russell's paradox and the other paradoxes of set theory. Nobody has been able to find a logical contradiction in ZFC. The next axiom is a straightforward one, which states that given any two objects, there is a set containing both. And this is called the axiom of pairing. For all x, for all y, for some z, x in z, and y in z. The next axiom states that given any set of sets F, there is a set containing all elements of F. And this is called the axiom of union. For all F, for some A, for all Y, for all X, if X in Y and Y in F, then X in A. So A is the union of the elements of F, and here Y is standing in for some arbitrary element of F, and X is some arbitrary element of Y. And I'll read the statement inside the quantifiers again. If X in Y and Y in F, then X in A. Okay, so we call the set containing exactly the elements of F the union of F. The axiom of union does not in itself state that the union of F exists. One can prove that the union of every set exists in ZFC by applying the axiom of union, which yields a set containing all elements of F, and then applying an axiom of specification to narrow down to a set containing exactly the elements of F. For this purpose, one can use the axiom of specification for the statement for P is equal to for some A, X in A, and A in F. Okay, after the axiom of union comes another axiom schema, another infinite set of axioms. This schema, the axiom schema of replacement, tells us that the image of any set under the image of any definable function is contained in some set. A definable function, for our purposes, is a statement P relating a variable representing the input of the function, namely x, to a variable representing the output of the function, namely y. For a statement P to be a function over a set A, it must be the case that for every x in A, there is exactly one y, such that P. An example of a definable function is the statement P is equal to for all z is in y, if and only if z is equal to x. This statement defines the function that maps any object x to the set y containing exactly x. The image of a set A under a definable function P is the set of all y such that for some x in A, P. In other words, it is the set resulting from collecting all of the output values that P produces for input values in A. The axiom schema of replacement states that the image of any set under any definable function is contained in some set. Formally, let P be a statement of first-order logic in the vocabulary of ZFC, which does not contain any free occurrences of the variable name B. Then the following is an axiom of ZFC. For all A, if, for all x, if x in A, then for exactly one yp. Then, for some B, for all x, if x in A, then for some y in B, and p. Okay, so let me break that down a bit. So it's an if-then statement, and the if is a clause expressing that p defines a function, and so that clause is for all x, if x in A, then for exactly one y, p. And then the then part is stating, right, there exists a set B containing the image of P, and I'll repeat that clause. For some B, for all x, if x in A, then for some y, y in B, and P. Okay, and A here is the domain of the function. Alright, so in this axiom I use the quantifier for exactly 1, which is something that we haven't seen before, and it was not part of the definition of statements of first-order logic given back in the section titled Statements. A statement of the form for exactly 1x, q, can be taken as an abbreviation for some x, q, and for all y, if q with x to y, then x equals y. The axiom schema of replacement implies that there exists the image of any set under any definable function. The argument is a straightforward variation on the argument that the axiom of union implies the existence of the union of any set of sets. The next axiom is the axiom of ZFC, which allows it to prove the existence of infinite sets. If one removes this axiom from ZFC, then in the resulting system, it is not possible to prove the existence of infinite sets, and by infinite sets here I mean sets with infinitely many elements. Okay, so axiom of infinity. For some x, for some e in x, and not for some y in e. So that clause is stating that the empty set is in x. Okay, and for all y, if y is in x, then for some s is in x, and for all z is in s if and only if z equals y. And so this is stating, right, for every element of x, the set containing exactly x is, or the set containing exactly y is also in x, right? So for any element of x, the singleton set containing just that element is also in x. Or in short, x is closed under the operation of taking the singleton set. Right, so in total, right, the axiom of infinity states that there is a set which contains the empty set and is closed under the operation of taking singleton sets. Now such a set is infinite. But the real significance of this axiom requires some unpacking. So let's begin with the concept of natural numbers as they are most commonly defined in classical set theory. This is the so-called von Neumann construction of the natural numbers. Here by natural numbers, I mean non-negative integers, i.e. the numbers 0, 1, 2, 3, etc. onto infinity, but not including infinity. In the von Neumann construction, we equate each natural number with the set of smaller natural numbers. We equate the number 0 with the empty set, since there are no natural numbers smaller than 0. We equate the number 1 with the set containing exactly the empty set, or in other words, the set containing exactly the number 0. We equate the number 2 with the set containing exactly the empty set and the set containing exactly the empty set, or in other words, the set containing exactly the numbers 0 and 1, and so on to infinity. We may call the sets which are the natural numbers as defined and constructed in this fashion the von Neumann natural numbers. The axiom of infinity, viewed at a high level, asserts that there is a set containing all the von Neumann natural numbers. That's not exactly what it says, but that's basically what it's intended to allow you to prove. So the axiom of infinity asserts the existence of a set X, um, that contains the empty set and is closed under the operation of forming the singleton set. And this axiom serves as a precursor for fairly intricate set theoretical developments that lead ultimately to the conclusion that the infinite set of von Neumann of exactly the von Neumann natural numbers exists. So to do, provide a source. I know this is true because I've gone through the construction, in a mathematical logic course in grad school, but I need to provide a source here. Okay, so the next axiom, the power set axiom, implies that for every set A, the set of all subsets of A exists. This is called the power set of A. So a subset of a set A is a set B such that for all x, if x in B, then x in A. The power set axiom reads as follows. For all A, for some P, for all B, if, for all x, if x in B, then x in A, then B in P. Right, so this is saying, right, for any set A, there exists the set P. That's the power set of A, such that for all sets B, right, that are a subset of A, B is in P. Okay, so to clarify, right, P might not be exactly the power set of A, but it at least is a superset of the power set of A. Okay, and the final axiom, the axiom of choice, is a subject of much wonderment, controversy, and meta-mathematical research. So, quote from Wikipedia. Informally put, the axiom of choice says that given any collection of bins, each containing at least one object, it is possible to make a selection of exactly one object from each bin. All right, so that's odd. I don't know, this statement of the axiom of choice is so hairy. I don't even see much point in trying to read it out straight, but I'll dig into it and see how we do. Okay, so for all x, all right, what is x here? Well, if for all y, if y in x, then for some z, z is in y. Okay, so that's an if clause, and so for all y, if y is in x, then for some z, z is in y. Oh, so in other words, X is a set of non-empty sets. So that's the if clause. So let's go to the then clause. For some F, for all A, if A in X, then for exactly one B, A comma B in F, and for all B, if A comma B in F, then B in A. Okay, so in this then clause, we're asserting the existence of what's called a choice function, f. And this is a way of picking out an element from each of the non-empty sets in X. So f is a function, which is a set of ordered pairs. And so we're saying, right, for any element of X, A, there's exactly one B, such that A comma B is in F. So yes, that's saying that F is a function on X, right? It's well defined on X. Given any member of X, F will give you exactly one B. And then the final clause, right, states that B is in A. Right, so whatever input A you gave to F, it'll give you a set B such that B is in A. So it's a choice function. That's the axiom of choice. So in order to state the axiom of choice, I introduced a new notation, the ordered pair notation, A comma B. Conceptually, an ordered pair is exactly what it sounds like, a sequence of exactly two objects, one after the other. In classical set theory, ordered pairs are commonly defined by Kuratowski's definition, which equates the ordered pair A comma B with the set of A and B and the set of A. Or, in other words, the set containing exactly two sets, namely, the set containing exactly A and the set containing exactly A and B. Intuitively, this set can serve functionally as an ordered pair, because it tells us what both the elements of the ordered pair are, namely whatever elements are in either set in the Kuratowski pair, and it tells us which is the first element of the pair, namely whatever element is in a one-element set in the Kuratowski pair. I will not pursue further formalization of the ordered pair notation to avoid getting too distracted by details. But yeah, I mean, this is another instance where it would be good to have like a source of formal development of all this stuff that I'm breezing through to reference. The next notion the axiom of choice employs is the set-theoretic notion of a function. In set theory, a function is a type of set of ordered pairs. If f is a function, we can equate the statement f of a equals b with the statement a comma b in f. A function, by definition, is a set f of ordered pairs such that, for all a, if for some b, b in f, then, for exactly one b, b in f. So my formulation of the axiom of choice states roughly that for any set x of non-empty sets, there is a function f such that for all a in x, f of a in a. And that completes this presentation of the axioms of ZFC, which is heavily based on Wikipedia's presentation. Now from these axioms, together with the laws of classical logic, one can prove almost all widely accepted mathematical truths, almost all practically important mathematical truths, and in general, all mathematical truths known to humans, except for some esoteric or alternative mathematical truths. The known esoteric mathematical truths not provable in ZFC are often logical or set-theoretical in nature. One example of a mathematical statement not provable in ZFC, but widely accepted as true, is the statement that no logical contradiction can be proven from the axioms of ZFC. Another example of a mathematical statement not provable in ZFC, but widely accepted as true, is the statement that there is an inaccessible cardinal. That completes the introduction of mathematical notions, which is the first step in the argument I am currently presenting for the correctness of the rules of classical logic.